Hi everyone. How I hope everyone's doing well from wherever you're joining us in the world. We are at the head office of RBR Canada here in Ottawa, and we've got the wonderful backdrop of our R&D team working away. Today we are going to be talking about PAR and narrowband radiometry, and we're going to be introducing a new line of radiometers from RBR. Now, my name is Rob Lee, and I'm the marketing director here at RBR. I'm going to introduce Jon Taylor, sensor engineer. He's going to be coming on and talking a lot more about the sensors and what's making them tick. We have a couple of other surprise guests joining us. Before we're done, you're going to wind up taking a little bit of a tour around North America. So we're going to have some fun, and we're gonna pray the tech works. But so far so good. So you likely know RBR from CTDs, temperature, pressure sensors, tide and wave instruments, but we've also been manufacturing optical sensors for a while now, including an optode that we actually released about 5 years ago. PAR sensors are nothing new to RBR either. We've integrated third-party sensors for some time now, both cosine and spherical sensors, and for integration with our RBRsolo compact loggers, as well as the RBR Concerto and RBR Maestro loggers and CTDs. So now we're really happy to be offering our own line of PAR and narrowband radiometers, which really delivers a few advantages for us. We're focused on obviously providing great sensor performance, but also we have the opportunity to optimize the sensors for use with the RBR loggers. The other thing that we might not have talked about so much a few years ago, having our own line of sensors gives us a little bit more control as well over supply chain and a little bit more reliability and delivery, which is really timely right now with a lot of companies struggling with that. So we're doing what we can there as well. So today, we're gonna spend about 30 minutes with you folks. We're gonna talk about, and we're gonna go to Halifax with Matt DeVere, and he's gonna chat and give a quick overview of PAR radiometry in oceanography for an overview. Then we're gonna come back to Ottawa. We're gonna dive into radiometer design with sensor engineer Jon Taylor. And then finally, we're going to take a look at how the new RBR radiometers integrate with both the Solo and the Concerto logger platforms. So with Candace Smith, and she's actually down in sunny New Orleans at the AGU conference right now. So she'll be joining us from there. If at any point you have any questions while we're going through the webinar, just type them into the Q&A, and we'll be happy to respond. We'll get to as many as we can, and then after, if we don't get to them all, then we'll get back to you individually later on today. Now with that, I'm happy to turn it over to Matt DeVere over in Halifax. Go ahead, Matt.
Hey, hi everyone. So I am talking to you right now from sunny Halifax, Nova Scotia, and we're doing some surveying of the harbor. So I'm actually on the boat with my colleague Ruby doing all the work. But Rob asked me to talk quickly about what it means to measure PAR for oceanography and why we actually care about it. And as a quick introduction, I think being in the field is actually pretty great and pretty appropriate. So really, as we know, most of the things that grow in the ocean needs any photosynthetic organism need mostly light and nutrients, food, to be able to grow anything, right? And so measuring light in the ocean has been something we've been doing for a very, very long time. Traditionally, we stick a disc, which was just a black and white thing that we used to send down and see how far down the water can penetrate. Today, on a day like today, the sun just emits a wide range of wavelength in the water, but really there's only a range of that spectrum, just a range of wavelength that's interesting to whatever grows in the water, right? And so I would love to show you something growing in the water right now, except it's December and nothing really grows, exactly because we don't have much nutrients and we don't have much light because the days are pretty short. So measuring how much light is actually entering the ocean and how far deep it goes is very important. PAR is actually an integrated quantity where you measure the amount of light that's emitted in the water between 400 and 700 nanometer. And that's the range we care about the most, because that's really the range of wavelength that organisms use to grow photosynthetically. And so that's really the range that we want. So a PAR sensor tends to integrate the amount of light that's within that range, that part of the picture, while radiometers kind of select a unique wavelength and measure the light received at that specific wavelength. And so as the light penetrates the water, it tends to dim, right? It's harder and harder, it gets darker and darker as you get deeper. And so measuring how far the light goes down the water column is actually really, really important for any biological processes that people are trying to investigate. So the things we care about PAR sensors, I guess, is making sure that, first of all, it measures within that range of 400 to 700 nanometers and not outside of it, because we don't really care about any wavelength that's outside of that range because it's not used by the organisms. And it's also important for the sensor to be able to measure light, not by only pointing out directly at the sun, but also, if anything in the ocean is never gonna, be right directed at the sun. So you wanna make sure you have a wide range of angles where you can accurately measure how much light is coming in. And I think Jon is gonna talk a little bit more about this. So on that note, Rob, unless you have any questions, I can send it back to you.
Thanks, Matt. The one question that actually does come up fairly often is how far down and under what conditions will light penetrate? And given that depth, why are we building titanium sensors that will go down to 2,000 meters, far beyond where the light can measure? Maybe I'll put it back to you to answer that.
Yeah, people see that all the time. Why go through a table of a titanium housing if really light only penetrates, in the base places of a few hundred meters is the deepest it goes, and more often than not, it's much shallower than that. The reason why is that you might have a profiling platform, and so Argo, for example, is using PAR on their profiling floats, and it's very important to measure. It's part of the core biogeochemical variables that are measured by BGP Argo program. And those floats go down all the way to 2,000 decibars, so 2,000 meters in the ocean. So you want to make sure that you have something that sustains that range of pressure, even though there's no light down there, but you want to be able to measure it on the way up, and you want to be able to equip instrumentation that would go that deep. So yeah, I think that answers the question, Rob.
All right, thanks a lot, Matt. Really appreciate it. Yeah, it's really nice to see you out there on a really sunny day, and really appropriate when we're talking about PAR measurements. It's just unfortunate that the sun is so low on the horizon, which is the reason why you're wearing that warm jacket. Anyway, okay, with that, I'm going to bring in Jon Taylor to talk a little bit more about sensor design and specifically the RBR radiometers.
Excellent, thanks, Rob. Yeah, so what I have here is the heart of our radiometer instrument, and this would be integrated into the different variants of what we manufacture. For start, our standard instruments, such as the Concerto and the Maestro, these wires would feed directly into a connector, and then that would be cabled then into our instrument. And then the instrument converts the signal coming out of here into the engineering units. In the case of a compact instrument, these wires would be wired directly to a CPU, and then it's all logged internally. And in this particular instrument, it's our serial coda variant. The signal goes to our CPU, and then a serial converter then streams the data out to whatever you have on the other end. And so there are several elements to our sensor that gives it the exceptional performance. The first being the cosine response. You could show the plot for our cosine response there, Rob? Sure.
See that okay?
Yeah, so here we show the cosine response for our particular sensor, and our sensor follows a predictable cosine response within 5% up to an angle of incidence of 65 degrees. And we'll just drop that so I can show you the elements of the sensor that actually give us that response. Excellent, yeah. So the cosine response is primarily driven by the construction of the sensor face here. So you can see we have a black coating to minimize any reflection, and everything from the height of this diffuser, the little white dot in the middle, the width of this moat, the trough between here and the lip, and the chamfer on the lip are all designed to give us that nice cosine response. And we also have an excellent quantum par response as well. Can you show the next plot there?
Mm-hmm.
Yeah, so the ideal spectral response is a flat line. So across the full range that we're interested, that Matt referred to, from 400 to 700, and very sharp cutoffs, a strong rejection out of this wavelength range. So, and so we optimize the diffuser and the internal optics to give us the spectral response and this ideal par response. We also have a custom infrared filter in here, as well as other optical elements. And this gives us good rejection above 700 nanometers and below 400. And we also have a specially selected photodiode that gives us a nice overall response that's proportional to the photon flux, which is that nice flat response across the full range. Also, another important element is we have a large dynamic range of over 5 decades, and that's all achieved on a single gain. And to do that, we have a high precision amplifier, and this, as well as some careful analog design. And this is used to convert the current that comes out of the photodiode into voltages. And the amplifier is located right next to the detector, and this provides a strong buffered voltage. So the signal is immune to noise pickup, especially in the cabled analog version. And then to process the signal, we have a 24-bit sigma to delta analog to digital converter to digitize this analog signal with very high resolution and very good accuracy. And so what's unique to our particular radiometer is that we also have a temperature sensor embedded right next to the photodiode and the amplifier. And this allows us to do a temperature offset correction. And that brings us to the calibration of the instrument. So all of our instruments, they start with a temperature calibration. So we calibrate the thermistor that we're using for our offset correction across a range from -5 to 35 degrees to give us this nice dark offset characterization. And then after that, we move on to the optical power calibration. So we use NIST traceable references for the whole calibration. So we start with a source. So we use a combination of a NIST traceable FEL bulb as well as a solar simulator. And the solar simulator is really neat because it shapes the spectrum that comes out of the light source to match that of our sun. And so we measure all of these sources with our NIST traceable thermal and silicon power meters. And after all this calibration is done, on top of that, we also do a pressure test to make sure that whatever rating the pressure the instrument's rated to, that we ensure that there's no faults in the assembly and it'll survive to that pressure. And lastly, our design, it utilizes very standard filter sizes so that we can easily add new radiometer wavelengths to our suite of instruments that we offer. And currently we have 7 different offerings in narrowband radiometers. These range from 413 nanometers all the way to 560. So a nice suite there.
Well, that's great. Thanks, John. Wonderful. Okay. Well, with that, you can see like John's kind of covered the business end of things in terms of the sensor. What really allows you to simplify, though, par radiometry is how this sensor integrates with our Solo compact loggers and our Concerto and Maestro CTDs. And for that, we're going to pitch it down to Candace in New Orleans, who has all our demo gear down at the AGU and happily will show us and give us a guide and walkthrough of that. Go ahead, Candace.
Awesome. Thanks so much, Rob. As Rob mentioned, I'm here in New Orleans and I'm normally in Halifax with Matt. So I'm very proud to be outside right now, not wearing a jacket. So I'm very excited to be doing that as a Canadian in December. So this is great. Yeah, so today I'm actually going to talk about our different variants that you can integrate of the par and the radiometer. So John had showed a CODA variant. So that's our serial CODA variant. So one thing I should start with actually is to say that So many of the features for the PAR and the radiometer are all the same great features that you're used to with RBR. So we have the same serial coda variants now with PAR and radiometer. Maybe you're used to that with temperature or pressure or even oxygen, as Rob mentioned earlier. We have things in the compact solo version, and we have things, I have a concerto next to me. I'll show you what that looks like if you integrate the PAR onto a CTD. So all that being said, I'm going to start sharing my screen. Awesome. Here's my screen. So the first thing I'm going to show you is, so first of all, if you don't know, I don't know, maybe you're brand new to RBR, this is Ruskin. It's our free software. You can operate it on Mac like I am today or on PCs. So it's free. You can go to the website and download it, and you can actually simulate instruments. You don't actually have to have live ones like I do today, but I'll actually show you because I don't have a coda variant sitting next to me. So I'm going to go to instruments up here and simulate an instrument. And then the coda line, we call those sensors. So I'm going to go over here to the sensor panel. And then you can see we have a lot of different flavors, some T's, some DOs and everything. And I'm going to actually simulate the coda rad right now. John mentioned we have 7 different flavors, I like to call them, and 7 different variants. Just note that it doesn't matter what variant you're using, the power is exactly the same. So that's why it's gonna, you don't have to like pick, I want the 413 band for this. And just for fun, I'm gonna add an option of fast 16. So again, if you're new to RBR, you might not know what these fast features are. The fast 16 means you can sample up to 16 hertz. So you don't have to do 16. And if you leave it at this blank one here, it just means up to 2 hertz. So you can do anything from once a day to 2 hertz. So that's 2 times a second. That's about as fast as I'm talking right now. So I'll try to slow down. So here we go, 16 hertz. Okay, so I'm gonna hit the OK button. So I don't have an instrument connected. This is all Ruskin doing, again, what we call a simulation. So you can see here that I have some different options. I can change the rate. So I said up to 16. So you could actually pick 4 hertz instead. You can change the baud rate over here. And you can, if there's anything that about the instrument that needs to be updated, you can actually do that in here as well. And again, if you don't need that often of a sample, you can sample, you can put say 1 minute in here, like that. So let me just see if the data is coming in. So Ruskin will also, because I simulated a sensor, we should be seeing some data popping up. My computer's a little bit slower today than normal. Let me see if I can change this back to fast. Then, if that will help. Okay, well, that's fine. It's not showing it. It'll pop back up, I think, when I stop sharing. So that's the coda version. So that's the sensor part. So the next I want to show is the sensor. It's an analog sensor that goes on our L3. So that's the standard instruments. Again, if you're used to concertos or maestros, they're the white body instruments that have 8 AA batteries. So I have a CTD here. So you can see the conductivity, the temperature, the depth, and then we have 2 connectors here. So these are for cabled sensors. So you can see I have a cable here. I'll just talk a little bit about the logger itself. So it has the same great twist activation that we all know and love. So you just twist to the run, it's gonna buzz. That tells me that now it's actually collecting on all the channels at the same rate. And it actually kicked on the Wi-Fi. So my phone is next to me. I can open up the Ruskin app on my phone and actually get the data in real time, which is really awesome. So I'm just gonna twist this back. And now here, I'm gonna show you what our sensor looks like. So this is much shorter than the one that John had showed you. So it makes it a lot easier to actually mount it onto this logger body. So this is analog sensor, and then this is just one of our cables. So essentially you have something that looks like this, and we would clamp the sensor onto the logger body, and we would likely want the sensor facing upward. If you're profiling downwards, you can see you're measuring the light coming from the surface. So that's how the PAR or radiometer would work in an L3 body. So that's awesome like that. Yes, and now I'll show you the last version that we have. Well, not the last version, there's many different permutations. But again, you may be familiar with this smaller version, the Solo or even the Duet product line. The non-titanium version is yellow, so you might have some of the yellow loggers. So again, a lot of the awesome same features that you're used to with RBR. So excellent electronics, small body, AA batteries. So you can see in here, again, it's the same sensor that John was showing earlier. And I'm just going to open it up and show you again. if you're used to solos, it's exactly the same as the inside of your solos. So I'm gonna put the housing over here so I don't lose it. Okay, so we have the USB-C, again, a cable that is really easy to get. It's not a custom cable at all, so you can find it in your local shops around if you need it. We have desiccant. Some of you may not have seen this desiccant before. It's pretty new. Orange is great. If it goes to dark green, that means it needs to be changed. And actually, you might be able to see there's a little cap here. They're rechargeable now, so you don't have to throw them out. You can actually reheat it and get them back to this bright, beautiful orange color to know that things are good. And then one AA battery here. So this is a lithium ion battery for the sensor. So again, if you open up a Solo T, you're going to see the exact same stuff inside, maybe a different flavor battery. So it's all the same great RBR. Oh, I don't want to close that, RBR instruments. Okay, so actually I'm going to open this up. I'm going to plug this in because I have Ruskin running, and I'll show you what this looks like when you have a real instrument. So plug that in. Okay, there's all the data. The code I was showing, I'll show that now too. I'll share my screen. So I'll just go back. So this is what the CODA data looks like when you simulate. So I'm going to actually close that one off. So it's not so distracting. So I plugged the instrument in. This is a real instrument. It actually works. I'm going to take the cap off too. So it's plugged in, it's recognized what instrument it is. It pulled up the serial number. I didn't have to do anything special. One thing that Jon mentioned as well that I want to highlight is we actually give you, he calls them engineering units, I call them the actual units, like what you actually want to see. Voltages are fine, but getting the actual value is really awesome. So RBR always does that. We give you the real units in terms of temperature, salinity, or conductivity, and in par here, you can see what the units are, which is really great. And then here, this panel looks a little bit different than the CODA because there's a battery and memory inside of this logger. So you can actually pick sort of what sampling rate you want. And then it tells you how long the batteries will last, basically, or the battery. In this case, it's one battery inside. I can pick UTC time or local time. And then you can start it. And all I have to do is enable, and it'll start collecting the data right away. Enable that. See. And now it's ready to go, and it's measuring already. It's saying logging in progress, so I can see everything. I'm just trying to see if I can. So it's sampling at 1 second right now. There we go. And then if I close the cap, actually, you should see that it's going to shoot all the way down to 0. There we go. So I'm going to stop that. And I'm going to stop here too, because if I don't, I'll forget that it's logging and it'll just log with a cap on it forever. So that's it. It's pretty simple. Like I said, it's all the same great features that you're used to with RBR. Now we have it for PAR and radiometers. So I'm going to throw it back to Ottawa, where it's not nice and sunny, and you definitely need to wear a parka. So back to you, Rob.
All right, thanks a lot, Candace. That was an excellent walkthrough there. The one thing I'm going to ask Jon about, 2 questions that came up on the simulation there on Ruskin. It looked like some pretty jittery data, and so that's definitely a simulation. Whereas when you showed the data from the coming in from the PAR, the Solo PAR, RBRsolo PAR, it was much smoother. So with our simulations,
yeah, so the simulation is actually because there's no real instrument connected. So just to give you an idea of what the plot will look like, we actually just have a random number generator in there. So that's why it's such a radical spread, and that's where it's coming from. So that's why they don't look like any normal values. It's just kind of a nice way to see what a trace would look like as it's being fed in from an instrument.
Nice. And so I wanted to ask you about something else too that came up on questions. You mentioned temperature compensation, but didn't go into any detail. Why is temperature compensation important?
Yeah, so actually, when you receive a calibration certificate for an instrument, it'll show you the correction we're doing across that low temperature range. And the values will be very tiny, especially when you think about the full range of these sensors into like the 5,000 micromole. But there's a lot of scientists who are actually very interested in areas of the ocean that are very low light levels. And down there, when you're dealing with only a very small value, those offsets that we're doing at temperature are actually quite significant. So it's definitely much more important for when you're looking at the very low light level environments.
Okay, great. So I think we've covered most of the questions, and we're coming up on our half hour. So hopefully you enjoyed that. We took a little trip around North America, which was really nice, and had a chance to learn a bit more about PAR if it's new to you, or go deep into what the sensor technology is if you understand PAR and been measuring it for a while. I'd just like to say thanks to Candace and Matt as well and Jon for coming in and joining us. All these people are really busy, and Matt isn't staged. Matt's actually out there doing some research, so it was great of him to be able
time to go back to work now.
It's a great show. So anyway, with that, we'll sign off, and thanks very much, everyone. We really appreciate it.